Hello, everyone. Welcome to lecture number 19. The topic for today is antiderivatives and initial value problems, which are very much related. This is the symbol or equation for today. We're basically introducing the topic of integrals, though this is what's called an indefinite integral, and really we should be calling it antiderivative. So what is this all about? Very simple, an antiderivative of a function little f is a function big F such that the derivative of the big F is little f. This is the definition of antiderivative. Usually we're going to talk about them using these symbols right here. The big F is the antiderivative of the little f. So for example, if you have a little f function that is 3x squared minus 2, we all know how to take the derivative of that, which is f prime. But this is not what we are doing now. We are doing the reverse process. A possible antiderivative is this big F function here, x cubed minus 2x. Why? Because if you take its derivative, you find the original little f that you started with. That's why. But also another possible antiderivative is this one right here. I'm also calling that big F, by the way. I should probably have used a different letter, but the difference here is that I added a plus 5. You know that when you're taking a derivative, that's going to be irrelevant. The derivative is still going to be the same little f that we started with. So you can see that the same function can have more than one antiderivative. So as I said, finding an antiderivative is the reverse of differentiating, which means finding a derivative. And the remark here, we say an antiderivative instead of the antiderivative because there is always a family of possible ones, as we just saw. If you found one antiderivative, you can get others by adding a constant to it. So big F plus C for any constant C. Now, it actually happens that for most of the cases that we are interested in, these are going to be all the possible ways that you can get an antiderivative. So over an interval, at least, if you're always talking about a domain that's one interval, could be interval containing infinities, like the whole real line, for example. This is an interval, this is an interval. So if you have a domain like that, then it's true that once an antiderivative to some function little f is known, maybe let's call that big F, an antiderivative of big F. Once that is known, then the entire family of antiderivatives is obtained by adding a constant. So more precisely, we can state that as a theorem. Let little f be a continuous function with a certain interval I as domain. Then there exists an antiderivative, first of all, big F. And furthermore, every other antiderivative is of this form. You just, once you've found one, you can find them all by adding a plus c, any constant, c, a constant. All right, so this theorem not only, it's telling us when can we find an antiderivative, how do we know it exists? You just need the function to be continuous. Then there exists an antiderivative. And then if it's over an interval as domain, you can find all of them by adding a c, adding any constant. And finally, some bit of notation before we go to examples. The symbol for an antiderivative of a function, little f of x, is this symbol right here. And the first part of it is funny. It appeared in history as a variation of the letter S. This funny symbol is called an integral, more precisely an indefinite integral. We're going to see more about why later when we actually talk about integrals. For now, you think about this symbol as meaning a function. And you think about the funny s on the one side and this dx on the other side as kind of almost like parentheses. They go around the function f of x. They should always happen in this order. And for example, if you're talking about a function of a different letter, f of t, then the integral would be denoted by integral of f of t dt. This means an antiderivative just in the same way. So we can go to examples now. I have a bunch of functions here where we want to compute. technically we are computing integrals, but we want to think of these guys as antiderivatives. That's what they are. So in each one of these cases, we have a function between parentheses. That's going to be our little f. And we're trying to find a big F whose derivative is these guys. And we can do these right here. It fits on this box. These are not very hard ones. For example, what is a function whose derivative is 5x to the fourth? You should agree that's x to the 5 because of the power rule. Because when you differentiate x to the 5, that's exactly what you get, 5x to the fourth. And I'm adding a minus sign in front because there was this minus sign in front. Now, what about this x part? Can you think of a function whose derivative is x? If you try x squared, that's not really it, because the derivative of that would be 2x. But if you then add a constant like 1/2 in front, then that's it. The derivative of this function 1/2 x squared is x. All right, so this right now is not fully correct. This is just one example of a function whose derivative is the function given. We want to, the symbol means the family of all possible ones. So we have to add a c here, plus c. Any constant that you add here will still give you a function whose derivative is the original function. So this is the answer. Because by the way, if we don't say anything about the function inside of the integral, then the domain for that function should be whatever the domain is. In this case, every possible real number. So okay, now for item B, a function whose derivative is the number -7. -7 times x. That's just it, right? And now once you have this one function, you can get all of them by adding a constant. So the c could be the number 2, the number pi, whatever you want. Let's go to the next one. This one is a little bit tricky because of the 2/x. So we know a function whose derivative is 1/x. That's the ln function. And with this 2 here, you might think just 2 times ln of x. The only problem with this is that this function ln of x is only defined for positive x's, whereas here we're talking about possibly any interval of x's that it hasn't been specified. So you should try to remember that the derivative of ln of absolute value of x is equal to 1/x. We've actually seen this example before. I'm just going to write it down here as a remark, but we should remember this. Ln of absolute value of x derivative is equal to 1/x. We've computed this before, and this is true for any x different from 0. So if nobody is specifying where this function is supposed to be valid, you don't know if it's going to be the negative side or the positive side, so you have to put an absolute value there. So that was the tricky part. But now for the rest, what is a function whose derivative is sine? Well, the derivative of cosine is minus sine. But if we put an extra minus in front, then the derivative of minus cosine is plus sine. And then our usual plus c. All right, technically the domain of the function would not be an interval because we're only excluding the number 0. So it's 2 separate intervals, but it's okay. Usually when this happens, you are implicitly talking about just one of those 2 intervals. So the plus c is still just there, just 1 plus c, and that's enough. I'm talking about let me go back, the specification in the theorem that this has to be an interval as a domain. If nobody says anything about the domain of the function, you just assume it is an interval. And in this case, we don't know if it's the positive or negative x's. So we have an absolute value in there. Okay, so technicalities, but important thing is to understand how to obtain these functions. Next one, you see that I changed the name of the variable. Now it's a y. But what is a function whose derivative is e to the y? That is also e to the y. A function whose derivative is minus 3/y to the fourth. Well, if you've been practicing these functions, you should recognize it. What happens if you try, this is a plus, if you try to differentiate 1/y to the cube? So that's the same thing as y to the -3, right? And by the power rule, the derivative becomes minus 3 times y to the minus 4, which is 1 over y to the 4, exactly as you have in the problem here. And finally, the last item, it's kind of a tricky question. I mean, trick question. It's the function is written in terms of y, but the variable of integration, if you want to call that, it's x. So we are trying to think of this function inside as a function of x. It's just a constant function. Y with respect to x is a constant, is a number. So item E is actually like item B, where you have the integral of a number. And what is the answer there? It is that number times x. So this is the function whose derivative with respect to x is equal to the number inside. And then you add a c. So you're, of course, unlikely to have something like this on an exam, for example. That wouldn't be very fair unless there's a reason to ask this. Just pay attention to what is your variable. Okay. So by the way, I haven't mentioned this, but finding antiderivatives is usually difficult, if not impossible. It's not like derivatives where we always have a rule to find a derivative no matter what you write down. These guys are not usually not so easy. The ones that I gave in here are very easy. We look at these functions and we immediately recognize where they come from. But that's not always going to be the case. And one of our goals in this course is to get to a point where we can do it for many cases, but it's not possible to do for all. But all right, we have some useful rules, and the first one here we probably already realized. These are called linearity. So if you have two continuous functions on an interval, for technicalities, of course, and then multiplied by constants a, b, and you put this particular combination inside of an integral, then what happens, you can basically take the integral separately only on the f function and multiply it by that corresponding constant, and then also only on the g function, multiply it by that corresponding function. So I'm going to go back quickly. We've basically already done that right here. For example, when we were integrating 2 over x plus sine x, we integrated each part separately, multiplied by the corresponding constants, which are 2 and 1. So we've done this already. And I have just one more example here. So when you look at the function minus 4 secant square x, what is a function whose derivative is secant square? You just have to remember that it comes from the tangent function. And you just keep this minus 4 in front. So just like that. Minus 4 tangent. And then the antiderivative of the other part, plus 7 cosine. Well, keep the plus 7 as a constant. And what is the antiderivative or a antiderivative of cosine? That would be sine, because the derivative of sine is cosine. And then you can add a c. I mean, you have to. This is the answer here. So by the way, for you to remember something that can be useful, I've told you this before. If you draw the unit circle and you write sine minus sine, cosine and minus cosine at these particular places, I've told you how you can remember that derivatives go clockwise, right? So all of these guys are ddx. So for example, the derivative of minus sine would be minus cosine. Now you should always also remember that the integrals or antiderivatives go the other way. So, I mean, it makes sense, right? Because it's the reverse process. This is a useful diagram to remember when you are integrating or differentiating sine or cosine, because it can be tricky to remember where do you need a minus and where do you not need a minus. So we can keep this in mind. Okay, moving on. There is something that's called the power rule. It is called the power rule because it is the reverse of the power rule for the derivative. If you have trying to integrate a function that's x to a power, and if that power is not minus 1, then the integral is given by this formula here. You are going to add 1 to the power and then divide by that same number, r plus 1. And as usual, there is the plus c. Why? Well, because there isn't much to be proved here, right? Why is this formula true? Because the derivative of this function is the original x to the r. As you can check, this function prime, how does that go? Well, the 1 over r plus 1 is just a constant. It remains there. And you're really just applying the prime to the x to the r plus 1. And by the power rule for derivatives, this is what you get, r plus 1 x to the r. You see that the r plus 1s go away and you just get x to the r in the end. So this is a quick justification. But more important, why r different from minus 1? Well, if r is minus 1, this formula would not make sense. You cannot divide by r plus 1 because that's 0. So this formula does not make sense. And how do you actually find then the antiderivative if r is equal to minus 1? I'm going to write that down here before we go to the examples. Remark, what if r is minus 1? So in other words, we're talking about the integral of x to the minus 1, which is the same thing as integral of 1 over x. What is that? We've already mentioned that. ln of absolute value of x. That's the function whose derivative is 1 over x. Let me make this absolute value more straight. Okay, so just remember that the power rule does not hold for -1 exponent. If it's this power rule right here, the one for the antiderivative. The one for the derivative is okay, it always works, any exponent. So quick examples here. You have a few power functions with certain coefficients in front. What is the integral of pi over 2 times x to the 4th? Well, you leave the pi over 2 in there, and then to integrate x to the 4th, you raise 1 in the exponent, becoming 5, and you also divide by that same 5. Don't forget the plus c. That's it. You can check, you can try to, whatever you find here, try to think about its derivative. It should give you the same original function. Next one. So we have the number 6 here. How do we think about 6 as a power of x? Well, not 6 itself. 6 is the constant. But you can think of this as 6 times x to the 0, because x to the 0 is 1. And then similarly, the square root is x to the 1/2. So these two things that we are trying to integrate here, they are powers of x. And we can apply the power rule. So in the first one, leave the 6 outside. And how do you integrate x to the 0? Should be x to the 1 over 1. In other words, this is going to be 6x, as you probably had already guessed. 6x is the function whose derivative is 6. Now what about x to the 1/2? So you want to do x to the 1/2 plus 1 divided by 1/2 plus 1. So let's clean this up. I'm going to pull an arrow here. I guess it does not really fit there. But this will be 6x plus. So 1/2 plus 1 is 3 over 2. Similarly, you have a 3 over 2 in the denominator here. I'm going to write that as 2/3 in front. So this is what it is. And I guess, as usual, add the plus c. All right, so finding it with root functions, cube root or whatever, some nth root of x to the m, things like that are possible. Finally, the last one, the variable here is called t instead of x for whatever reason. How does this one go? So you have a -8 as a constant. You can leave that outside if you want. And then really the only function that you're trying to integrate is t to the -4. The power rule says that this will give you t to the -4 plus 1 divided by -4 plus 1. -4 plus 1 is the same thing as -3. And if you're dividing by -3, well, leave that -3 in there. There's a minus together with another minus outside. They're going to make a plus. So 8 over 3, t to the -3. Which you can write as 8 over 3t cubed. And don't forget the plus c. So that's the answer. And by the way, this is standard practice. You only usually you want to only write the plus c in the end. If you're calculating an integral like this and it's like a chain of equalities, you don't have to keep writing the plus c every time. You just add it to the end. That's perfectly acceptable. Or you can also just keep adding it every time. That's okay. All right, moving on. Watch out. I have to say this because I've seen students making this mistake. There are no general rules for products and quotients in integrals. And certainly in general, if you're trying to integrate a product of two functions, you do not integrate each one separately and multiply the results. That's just not true. Similarly for quotients, integral of a quotient is not the quotient of the integrals. Now for derivatives, we do have rules to find a derivative of a product and a quotient. It's just not going to be the case for integrals. There are no general rules. There are certain things that we can try. We're going to learn a few of them throughout the rest of the course. But in general, you don't do it this way. You have to be smart. You have to simplify the function somehow until you recognize that it becomes something that you know how to find an antiderivative for. So here I have an example. Compute the integral and see that the answer is not going to be this one, x to the fourth plus x over x squared, which is, by the way, just the antiderivatives of numerator and denominator. If you think about it, that should be easy to see. So we're just trying to show that how do you integrate a fraction? You do not apply the integral separately in each piece. You don't do that. Let's see how do we actually do this one. So looking at this function that we're trying to integrate, what do you do? Well, the trick here is to realize that this is a fraction where there's only one term in a denominator. We can split it up into two fractions. And because every single term here is a power of x, this is going to become a sum of powers of x. And the power rule takes care of that. So for example, 4x cubed over 2x plus 1 over 2x, this is the function that we have. You can simplify this. It becomes 2x squared for the first term. And then just 1 over 2x for the second. These are just two powers of x that we know how to integrate. We're going to be using the power rule here. So integral for the first one, leave the constant 2 outside. And then integral of x squared is x cubed over 3 by the power rule. Second one, think of this as 1/2 times 1 over x. 1/2 is a constant that you can leave outside. And then the integral of 1 over x, that's the only one that you don't do a power rule with because it's x to the minus 1. That's at ln of absolute value of x. So these are the antiderivatives for each term, and you have a plus c representing an arbitrary constant. All right, by the way, you might want to think, why do I not have a plus c for the first one and then another plus c for the second one? I mean, you could have done that. We could have added a plus c1 for the first and a plus c2 for the second functions. But when you do that, these are arbitrary constants, and you can always combine them together into just one constant. So because they are arbitrary, because it represents any possible real number, they can always be combined when you have a sum like this and just made into one big plus c in the end. So you see that the answer that we got was completely different from what you might have thought would happen. Moving on. Just a quick remark about notation here. Usually when you write an indefinite integral, the symbol dx, that's called the differential part of the integral, we imagine that it's multiplying the rest of the function. So for example, you can write this symbol. I had a typo here. I had to write this x by hand, but I hope it's okay. Instead of writing integral of the function 1 over x dx like this, which is also fine, you can also imagine that dx is a symbol that multiplies this function, and you can multiply it with the 1 in the denominator. So it becomes dx over x. Okay, so this just means the same thing. It's symbolic notation. Either one is fine to use. And so, for example, you will see that when we have integrals involving a sum of two functions, like this, for example, I will usually write the parentheses because I want to imagine that the dx is multiplying the entire function. But not everybody does that. So this is up to you, really, using parentheses or not. I prefer to use it, but that's okay if you don't. But yes, this is just a remark for notation. Here's a slightly more complicated integral. The variable is being called z, and we have a looks complicated expression. We have a product in the top, and the whole thing is a fraction. But what do? Remember, you have to expand out, simplify as much as you can, until you recognize that it is a sum of functions that you know how to integrate. And the reasoning is the same as the example before. Everything here is a power of z. So after you expand everything out, everything is still going to be a power of z. Okay, so I'm going to denote my z like this, a cursive z, because this one kind of looks like the number 2, especially if I forget the little dash in the middle. So I'm going to be using this for z. But what does this integral become? Let's distribute the top. You have z to the 4th plus z cubed times 2 over z gives you 2 over z squared. Sorry, 2z squared. Yes. Now minus 3z to the 4th times z is minus 3z to the 5th. And then minus 3z to the 4th times 2 over z should give you minus 6z squared. No, z cubed. Yeah, that's better. 4 minus 1 is 3. Okay, this looks good. The whole thing is divided by 5z squared. So now it's the same as one of the previous examples. Let's split the fraction into a bunch of separate functions. Z fourth divided by 5z squared just gives you 1 over 5z squared. 2z squared by 5z squared is 2 over 5. 3z5 divided by 5z squared, 3z cubed over 5. And the last one, minus 6 over 5z with the z in front. dz. Yes, all right. So now we can do each one of these by power rule. I guess I'm going to rewrite the first one so we really understand what's going on. The first one is z to the minus 2 with the constant 1 over 5 in front. The second one has a constant of 2 over 5, and the function can be thought of as z to the 0. The third one has a constant of minus 3 over 5. The function is z cubed. And finally, 6 over 5 with a z. Now we do each one by no integral anymore. Now we are taking the integral. We're going to do each one by the power rule. Z to the minus 2 plus 1 over minus 2 plus 1. Z to the 0 plus 1 over 0 plus 1, and so on. I just wanted to do this very carefully, step by step. But eventually you're not going to be doing it always like this. You see this z in the last term is a z to the 1, so 1 plus 1 divided by 1 plus 1. Eventually, of course, when you see a number like 2 over 5, you're immediately going to get to the answer 2 over 5 times z. Okay, but what is this now? So we have a minus 1 downstairs. This is going to give you a minus sign in front. And upstairs, that's just z to the minus 1. Next, 2 over 5, 0 plus 1 is 1, z to the 1. Next, 3 plus 1 is 4, so minus 3 over 20, z to the 4th. And 1 plus 1 is 2, canceling with the 6 gives you 3 over 5, z squared. You can leave it like this, plus c, that has to be there. You can also just put the z in the denominator because it's to the minus 1 if you want. But this is the antiderivative. Here's the next one. Sine x over cosine x squared. So it's a fraction. We know that we're going to need to simplify it somehow until we recognize that this is a function whose antiderivative we know. In this case, you can think of it as 1 over cosine times sine over cosine. 1 over cosine is the same thing as secant. Sine over cosine is the same thing as tangent. And I hope you recognize this now. We do know of a function whose derivative is secant times tangent, and it's the secant function. So that's the answer. Now let me just point out, what if I had a sine square as well? So if I had an extra sign at the top, this would be tangent squared then. It's tangent times tangent. What do we do? The answer is we're pretty much lost. We don't know much yet. I mean, at this point still in the course, we don't have much to do there. We're going to learn how to simplify that. So right now, you should be aware that the functions that you know how to integrate are very limited. And changing just one little thing about them might change the result entirely to a point that you cannot even compute it. Okay, let's just change topic a little, change emphasis. A quick mention about graphs. So here's a fact. Since the antiderivatives of some function, little f, over an interval, all differ by a some constant c added in the end, then the graphs are always going to be vertical translations of one another. So in other words, if you found one antiderivative of a function, and then you found another by adding a c, what is the difference between these guys? And if you're thinking about their graphs, this plus c just creates a vertical translation. So graphs of antiderivatives, they all look alike. The only difference is the translation vertically. So now I have a problem that's similar to problems that we've done before. I'm giving you the graph of a little f function. Item A is asking, sketch the graph of a possible antiderivative. We're going to answer right here on the same graph. So let's focus on A first. I'm going to draw that in blue. Do you remember we've done problems where I give you the graph of a function and I ask you for the graph of the derivative of f prime. Now we're kind of doing this inverse process. We have the function, we want to find the antiderivative. But you just have to remember that the little f is the derivative of the big F, which is the function that we're trying to graph. So how do derivatives relate to a graph of a function? Where, well, the places where the little f, which is the derivative, is 0 will correspond to horizontal tangent lines of the big F function, right? Derivative equals 0. Little f is the derivative of big F. And similarly, the places where it is positive will correspond to, well, positive slope. In other words, so positive slope of big F. So in other words, an increasing function big F. And analogously, if the derivative is negative, you have a decreasing function, which means negative slope. Okay, so now when you look at the graph of the little f, which is in red here, we can identify certain locations where it is positive, locations where it is 0, and locations where it is negative. On the same x values corresponding to those locations, you know what the big F graph is doing. You know what it looks like. So right here where little f is positive, the big F is going to be increasing because it's a positive slope. Now we don't know if it starts up there or maybe down here, but it's increasing. Let me just draw one possibility here, something like that. So an increasing graph. But now, right at this point, at x equals 0, little f is equal to 0. That means big F is going to have a horizontal tangent line. So right at that point, it's a critical point of big F. Connecting back to the terminology from previous lectures. Critical point, derivative is 0, so horizontal tangent line. And then between here and x equals 5, the little f is negative, so the big F is going down, has a negative slope. But up to the number 5, when x is 5, little f is again equal to 0. So at that point, we're going to have another critical point. So going down until x equals 5, another critical point. Another place where the derivative is 0. And after that, little f is positive, so big F is increasing. And that's it. So if you go back to item A, notice that they are saying sketch the graph of a possible antiderivative. This is one of them. Now they're saying in B, sketch the graph of the antiderivative that satisfies big F of 0 equals 3. So now I've also given you one possible, one location of the graph for the blue graph. I guess I'm going to draw that in green. So this one is item A. For item B now, so this one will start at f of 0 equals 3. Other than that, you'll know that the shape has to be exactly the same. The two graphs are just a vertical translation of one another. So here's the answer to item B. You can see that the blue and the green just translate vertically to one another. All right, so this is illustrating the fact that if you know one initial location of the antiderivative, then you should have enough information to find everything about it, to know exactly where the graph goes. If you don't know that, then you don't know which vertical translation you're talking about. It could be anyone. So this connects us to the next topic. This is my last slide here. Finally, if you remember in the title screen, I told you this is another topic for today, initial value problems. We're going to call them IVPs. What is an IVP? An IVP is a system of equations, two equations actually, determining an antiderivative of some function. Notice that I'm going to be calling the antiderivative little f now instead of big F. Again, this is standard notation. If you see the book problems, they also do that. You can call functions whatever you want, of course, but just try not to be confused by this. Now we are calling the antiderivative little f, and the function itself that we are taking the integral of will not be called anything. Okay, so what do we mean by this? The first equation is going to be of this form. F prime equals some expression. Look down here. This is the one that's called the differential equation. And then the second equation is going to be something of this form, f of a equals b. So called the initial condition. So something like this. Okay, so what is solving an IVP? Look at the examples here. Example A. The solution is the function in this case. It's a system of equations, but we're not trying to find x or a variable. We're trying to find the function, f of x. And the system is telling you that the function has this derivative, x fourth plus 3. And its value when x is 0 should be the value 2. So in other words, we are looking for an antiderivative of the function x4 plus 3, but not any one, the one that has the value 2 when the x coordinate is 0. So this part, the second part here, specifies which one of the possible translations of the graph we are taking. With this information, you have enough to determine what the function is. And it's just that the function is being called little f instead of big F. Okay, so what is the little f? You start by doing this. It should be an antiderivative of this function. Okay, because the derivative is that function. So calculate this. Antiderivative of x to the fourth is x to the 5 over 5. Antiderivative of 3 is 3x. And there is a general plus c that we don't know yet. But now we have enough information to find it because we know f of 0 is 2. So with that, on the one hand, f of 0 is 2, and on the other hand, plug in 0 into the formula that we just found. So you have 0 to the 5 over 5 plus 3 times 0 plus c. That's just c. So look at this. We have just found the value of c. The initial condition is always used to find the c, the translation. So your solution, the function that you were looking for, is this one. This is the, sorry, c is equal to 2. This is the only function whose derivative is x to the 4th plus 3 and has a value of 2 when x is 0. This is all what an IVP is about. We are going to see some applications of this later. But for now, think about it just this way. So we're going to do item B here, and we are done. Look at B. G prime is supposed to be x minus 3 over x. And G of minus 1 is 4. So from the differential equation, you know that G is an antiderivative of the function x plus 3 over x. Taking this antiderivative is easy if you split the fraction as a sum of powers of x. So the antiderivative of 1 is x. Antiderivative of 3 over x is 3 ln absolute value of x. And there is a plus c. Now, how do we find the plus c? We use the initial condition. G of minus 1 is 4. So 4 is the value of the function when x is minus 1. This is now an equation for c. Let's solve this. 4 is minus 1 plus, well, 0. Absolute value of minus 1 is 1, and ln of 1 is 0. Plus c. So c is 5. And the answer to an IVP is the function itself. So you have to give me the function. This is the function, whose derivative is x plus 3 over x and has a value of 4 at the number minus 1. So I hope this makes sense. There are many problems like these in the book to practice. There's really no secret. It's about finding the c when you are given an initial condition, initial value for the antiderivative.